In this video, we're going to learn how the behavior of light gave some clues as to the structure of the atom when it comes to electrons. We know that there's a nucleus in the center of the atom that contains protons and neutrons, and the electrons are somewhere on the outside. And the place where they first started getting some ideas about where the electrons were and how they were behaving came from light and how light was interacting with atoms. To understand this, we have to first talk about the basic idea of vibrations, and we also have to talk about waves, which are related to vibrations. So a vibration is a stationary, periodic, repeating disturbance of some kind. Like here's an example. The drips that are coming from this faucet, they're happening on a regular, periodic basis. Looks like, once every 3/4 of a second or something like that, this thing is occurring. That's a vibration. Vibrations can be characterized by their frequency, which is abbreviated by the Greek letter nu, which I'm going to most often write as something that looks like that, kind of a tail, backwards tail on a V. That's a Greek letter, and it's the letter that stands in for frequency, which is how often a vibration repeats itself. The unit of frequency is the hertz, and a hertz is one happening, one vibration, one cycle, one anything, per second. A wave is a traveling, periodic, repeating disturbance. So vibrations often cause waves. So here's our dripping faucet in a tank of water, and that vibration causes the ability for the disturbance to travel as it moves across the crest of the waves. So a wave is a traveling, periodically repeating disturbance. Waves have a characteristic called wavelength, which is abbreviated by the Greek letter lambda, and that's the distance between wave crests. And the amplitude is how far does the wave deviate from zero disturbance. In other words, it's the height of the wave. So on this little graphic here, we see the wavelength being the distance from one point on a wave to the exact same point on the next wave. So this, would start going like that. So we're going from the beginning to the beginning. Or we could also go from the top to the top, or from the bottom to the bottom of the next wave. That's the wavelength. And the amplitude is just the distance from here to there. That's the amplitude. Waves have a speed. And to get at how we can determine what that speed is, here's an analogy. Imagine that you have a train that's going past you. You're counting, and every second a car passes you. And then, the train comes to a stop and you measure, and the cars are all each 10 meters long. How fast is the train going? It's pretty easy to figure out. If cars are 10 meters and there's one going past you every second, that means the train is going 10 meters per second. So the length of a car is like the wavelength. And how often one passes you, well, that's the frequency. So the equation that will tell us the speed of a wave is the wavelength times the frequency. The kind of waves that we're interested in here are electromagnetic waves. Electromagnetic radiation is, we commonly think about it as light. Light is just one version of it. And it arises because charged particles generate a magnetic field when they accelerate. So in this simulation, we have a coil of wire that's hooked up to a battery, and you can see in the simulation the electrons moving through the wire. So they're being accelerated because they're going around a corner, and change in direction is one way of acceleration. You can see that there's this little magnetic field, these magnetic field indicators around there. And as I move this compass around, magnetic north is responding to the electromagnet that's caused by these coils. On this side, the south end, the white end, is pointing through the coil. If I move it over to this side, the north end is pointing through the coil. So there's an electromagnet that's set up by the fact that these charged particles are moving. If I switch the direction of the current, the direction of the magnet switches as well. So now it's the white that's pointing into the coil on this side. When I move it over here, it's the red that's pointing into the coil. Also, a magnetic field generates an electrical field when it accelerates. Here we can see as I move my magnet into the coil, when it's stationary, nothing happens. But when I accelerate it, by changing its speed or changing its direction, that's when I can get the electrons to begin to flow, and you can see that the light bulb lights up. So changing a magnetic field causes an electrical field, and changing an electrical field causes a magnetic field. If these fields are caused by periodic accelerations, then they vary in time, and then they also vary in space as a wave. Here's an example of one of the kinds of electromagnetic radiation, the radio wave. So at the radio station, there are electrons that are part of the metal in the transmitter tower that are moving up and down, and as they change direction, that's when they're accelerating the most. So they're coming to a stop, and then they're speeding back up. In the middle of that movement up and down, that's when they're accelerating the least. And at the times when they're accelerating the most, those electrons, which are moving charged particles, they're throwing off the largest electrical field. And then in the middle, they're throwing off the smallest electrical field that goes along with that. So there's a magnetic field. Actually, it's being caused by these moving electrons. And that magnetic field causes an electrical field, and that field is changing its direction and changing its size according to the movement of those electrons. Now, there's a radio receiver over on the little red hut over to the side, and that has electrons that are following that electrical field variation. And so that stimulates the movement of those electrons, and then that movement in the electrons is picked up as current, as electrical current that's varying, and that turns into a radio signal. So that's how that works. And it's moving through space, this electromagnetic radiation. The two are together, the electrical field and the magnetic field, right in phase. And so as they move through space, the variation in the sizes of these fields, they just track with each other, but they're 90 degrees to one another. And that's how the energy is carried in electromagnetic radiation, through these fields of electrical and magnetic forces. Electromagnetic radiation presents itself in a lot of different forms depending on the wavelength that's involved. And here's a little, it's called an electromagnetic spectrum that shows you the whole breadth of these things. As the wavelengths get longer and longer, the light gets redder and redder. And as the wavelengths get shorter, the light gets bluer. Now the light that we can see is this little narrow slice right in the middle. It's expanded because it's important to us because of our eyeballs, but we can only see from about 380 to 780 nanometers. So that's a pretty limited amount of electromagnetic radiation that our eyes are evolved to see. If it's longer wavelengths than that, in other words, if it's redder than we can see, that's called infrared. And there are radio waves that are even longer than that. So that's like FM, AM, police band, those kinds of radio waves. And then if it's too short for us to see the wavelengths, that's ultraviolet or UV. That's also present in sunlight. You know, you're supposed to protect your eyes from it and protect your skin from it. X-rays are even shorter than that, and gamma rays generally are even shorter than that. So as the wavelengths get shorter or longer, you have different types of electromagnetic radiation, but it's all basically the same thing. It's variations in these electrical and magnetic fields that travel together with each other. Electromagnetic radiation all travels at the same constant speed. It's called the speed of light, 2.998 times 10 to the 8th meters per second. So that's the speed of all of these waves. It's given a name. The name of the speed of light is c, so that's what 2.998 times 10 to the 8th meters per second is. We can use this to answer some questions, like this one says, what's the frequency of yellow light that has a wavelength of 625 nanometers? So remember that the speed of any wave is equal to the wavelength times the frequency. So the speed of light is the speed of these waves, and it's equal to the wavelength of light times the frequency. We want to know what the frequency is, so we'll solve for that. Frequency is speed of light divided by wavelength. So we'll plug in the numbers here. The speed of light is 2.998 times 10 to the 8th meters per second. And the wavelength that we're given is 625 nanometers. Now, nano means a billionth. So that's 625 times 10 to the -9 meters. So we wanted it in meters because that's the way the meters cancel. And then our unit of frequency will come out in hertz, which is 1/per second. And this comes out to 4.80 times 10 to the 14th hertz. So 10 to the 14th hertz is 100 million. So that means that yellow light, the vibrations that's causing it are happening, about 500 million times every second, which is pretty fast. Microwave ovens are a practical application of electromagnetic radiation that's kind of interesting to look at. Here's a single water molecule in the inside of a microwave, which of course never really happens, but it'll help us understand what's going on here. Let's turn the microwave on. The microwave radiation is modeled by this green line. As the wave starts to set up and there's a variation in the electrical field, and there's a variation in magnetic field as well, but the molecule responds to the electrical field changes. So the red spheres represent hydrogen atoms and the blue is the oxygen in this model. The red side of that molecule is a little bit positive and the blue side is a little bit negative. So there's a charge variation. So as the electrical field changes, so when the arrows are pointing up, that means positive is up. When the arrows are down, that means negative is up. The molecule finds itself spinning around to try and follow the change in the electrical field. Let's change our view. Now here's a bunch of water molecules in a line here. And when we turn the wave on, then the molecules start spinning, but as they do, then they start whacking into each other, and that causes them to not only spin, but move around inside of the container. Now let's look at a lot of molecules, like in a cup of coffee, for example. When we turn this on, there's a lot of spinning going on, and there's a lot more crashing around, and so these particles end up moving more and more rapidly because of the change in their spin and how much they're colliding with one another. And so that's how things get heated up. Water molecules and other molecules that are like water start spinning around because they're responding to this electrical field that's changing. And that's how a microwave heats up your food. While the phenomena of light can often be modeled by a wave model, it turns out that there were some instances where it didn't work very well. And one of the people who did some of the work that uncovered this was Max Planck, whose picture is shown here. So light doesn't always behave like a wave. Sometimes it makes more sense to describe it as a particle. Where we see this, one of the places where we see this is in something called the photoelectric effect. Here's a simulation of the photoelectric effect. So here, this is what the model is. There's a metal plate here. In this case, it's sodium. That's what I have it set to. There's a lamp here that can send any wavelength of light that we want at a variety of different intensities. So there's also the ability to detect current, because if electrons can flow from here to there, then you'll pick up a current in this little meter down here. The photoelectric effect was observed as a phenomenon where if you showed light on substances, metals are pretty good at it, in just the right way, you could get electrons to be ejected from the atoms of those metals. And that was called the photoelectric effect, because photo is light, electric is electrons. And so you could measure this by measuring this current. So let's turn this thing on. Right now the intensity is at 0%, so basically this light is off. And when I turn it on, and the light begins shining on the sodium plate, you can see it's ejecting electrons. Those electrons are flying across the little tube that they're contained in. And as they flow through that wire, a current is registering. Current is 0.050 or something like that. Let's change this to a different wavelength. Let's go up to 490 or something, 488 nanometers, okay? So here at 498 or 88 nanometers wavelength, kind of a teal color, and let's jack up the intensity to 100%. Now look at the electrons that are flowing through here. The current that we're getting is 0.016 amperes of current. Now, let's move to 180 nanometers. So this is a shorter wavelength. In fact, this isn't even visible. This is in the UV range, approximately there. At 100% intensity, what we get is 1.579, quite a lot more current. And you can see that visually by how many electrons are moving in the simulation as well. Now let's drop the intensity way down. Let's go down to like under 10%, 9%. If you look at the current, it's still 0.148 amps, which is quite a bit more than even at 100% we could get for 488 nanometers for the longer wavelength. And they were noticing this, and it wasn't making a lot of sense to them because they thought, based on the wave model, that the wavelength shouldn't matter. What should matter was the amplitude. Like a tidal wave, a large amplitude tidal wave that doesn't happen very often would do a lot more damage to your house if you're on the beach than low amplitude waves that had a high frequency that were splashing up against your house, once every few seconds. And so the wave model did not explain this phenomenon. And there was another thing that was a little bit weird too. If we go to a higher wavelength, like let's say 645 or so, way up in these kind of reddish colors, that's pretty close, we get no current flowing at all. And even if I jack the intensity way, way up, nothing happens. And it turns out that there's a kind of a cutoff here. As I slowly move this slider back towards higher frequency, shorter wavelength, there will be a color where we will first start to see electrons flowing, right there. So somewhere between 538 nanometers and 546 nanometers, there's a cutoff. And above that, in terms of length of wave, if the waves are longer than that, the photoelectric effect will not occur. And below that, the photoelectric effect will occur. So Max Planck and others, including Albert Einstein, who's pictured here, came to the realization that since light doesn't behave like a wave all the time, there must be another part of its nature that we also have to recognize, another way of modeling light, and that is as a particle. So they came up with this conception that the energy of a photon is proportional to the frequency. Higher frequency light, bluer light, is higher energy photons. So the particles that are coming out of that light, or that make up that light, are high energy particles if the wavelengths are short, if the frequencies are high. And redder light, the light that is lower frequency, longer wavelength, that has less energy. The constant of proportionality is called Planck's constant. That's that H number. It's 6.626 times 10 to the negative 34th joules times seconds. So if you multiply this by a frequency, which would be in 1 over seconds, which is what hertz are, then the seconds will cancel and you'll get the energy of this photon in joules. Now this is a very small number, and even though frequencies are quite large for electromagnetic radiation, when you multiply them together, you still have a very small number. So an individual photon does not represent a very large amount of energy. However, it turns out they come in pretty large quantities, and so it adds up. Let's talk about light and color. White light is made up of all colors. So the visible white light that we see, it's actually all the colors put together. And when you pass it through a prism, the different wavelengths bend at different angles, and that allows us to spread the spectrum out and see all the different colors. You've probably seen this before many times. There are reasons that light can be colored. One reason that you might see colored light is because whatever source is producing that only has that one color. So here's green light going through a prism. Coming out the other side, it doesn't split into any other colors because it's just green light. It bends, because all light bends, but there's no difference between how much one wavelength gets bent or another wavelength gets bent, because it's all green. It's all the same wavelength. Another reason that you might see colored light is because you have an unbalanced spectrum. This is an artist's color wheel, and if you go 180 degrees across the wheel from a color, you see what's called the color's complement. And if you take out the complementary color, that will unbalance the spectrum, and it will give you the complement of the color that you've removed. Here's another simulation that might help us understand this. If I turn on a flashlight that's only red light, then that means the only photons that are reaching this person's eye are red photons. So the signal that gets sent to their brain allows them to see the color red. The same thing for green. If I were to turn on only the green flashlight, they're only seeing green photons. Or blue, they're only seeing blue photons. But if I start to mix these colors, if I give them a mixture of green and blue photons, they're going to see this color called cyan. Or if I did red and blue, they're going to see magenta. Or if I did red and green, they're going to see this yellow color. If I do all three of these colors, red, green, and blue, then that person sees white. So this is all the primary colors that are mixed together, and they're seeing white light. Here's another look. I'm going to put a filter in place. And I'm going to select a green colored light. And the filter that I'm going to put in place is going to be red. So when I turn this on, green photons approach the filter, but they don't make it through because it's absorbing the complement of red, which is green. And so that never makes it to the person's eyes, and they don't see any color. If I change the filter color to the same color as the light, then it's absorbing the complement, which is red, but there is no red, so all the light makes it to the person's eyes, and they see that green color. By the same token, if I switch this over to red, the green filter won't let anything through, but the red filter will let all the light through. If I send white light at the filter, it's going to take out colors such that an unbalanced spectrum makes it through, and he sees red from the red filter. But if I change it to a green filter, the unbalanced spectrum is going to allow him to see only green. White light, as we have seen famously, appears as a continuous spectrum when you pass it through a prism. But light from excited atomic samples, it turns out, didn't have that same effect. They had a discontinuous spectrum. And that's where they started to get some clues about maybe where the electrons were in atoms. Here's an illustration. If you take white light, pass it through a prism, this is continuous spectrum light. You get the whole entire rainbow. Nothing missing, everything's there. If you take a gas of a pure element, or compound even, heat it up, it will emit some light. If you pass that light through a prism, you will not get the whole spectrum. In fact, you'll only get little pieces of it. Here we see like a half a dozen lines across the whole spectrum that show up from this little fake gas in this illustration. By the same token, if you have a cold gas and you pass white light through it, it'll give you all of the spectrum except those colors. So it emits those colors when it's hot, but when it's cold, it absorbs those colors from white light and leaves them out of the spectrum. Those are called discontinuous spectra, or line spectra. And they were looking for clues about that. Here are some examples that you've seen probably before in your life. This is the spectrum of neon. This is the line spectrum of neon. So you heat up a sample of neon, send it through a prism, and this is what you would get. Example in real life, neon signs. Neon signs, when they're not painted with any other color, have this kind of a pinkish color. Why? Because what's missing from the spectrum is lots of blues and greens, and so the spectrum is unbalanced toward pink. Here's sodium's line spectrum. There's only two visible colors. They're both kind of yellow. Sodium street lights, sodium vapor street lights, are very common. You can still see them around some places. They look yellow, of course, because there's nothing else in the spectrum. Here's another one, copper. If you put a copper material into a flame, which you can sometimes buy to put in campfires and stuff, it looks kind of greenish. Why does it look greenish? Because if you look at the line spectrum, what's missing? The complement of green. There's not very much red or orange or magenta in there. And so you're seeing a spectrum that's unbalanced towards the green. Hydrogen was of particular interest because its visible spectrum is pretty simple. There's just 4 lines that most everybody can see, and there's some fifth line that is visible to some people. And hydrogen is the simplest element. It's got only 1 electron and 1 proton. So they figured if they're going to try and figure this whole thing out, hydrogen might be a pretty good place to start. There's a guy named Rydberg who studied these lines, not only these visible ones, but also some that existed in ultraviolet and in the infrared. And he found out that there's a pattern here. For any line that you could see, any wavelength that would actually be showing up in the spectrum, 1 over that wavelength would be equal to 109,737 inverse centimeters times 1 over some number squared minus 1 over some other number squared, where the only stipulation was n1 and n2, those 2 numbers in the denominator of that difference. Those would have to be integers, and the second one would have to be a bigger number than the first one. But you could pick any 2 integers, stick them in there, and that would predict the wavelengths that you would be able to see in hydrogen spectrum. This is like a law. Nobody had an explanation for it, but as they began looking for explanations, it looked like these discontinuous spectrum that they were seeing from pure substances had something to do with 2 different levels of energy or something inside of the atom, not 1. And that's really gave them some insight that helped them understand what was going on when they started looking for 2 different states, that the difference between them had something to do with the wavelengths that were visible. So here's a kind of a model. Say you have energy on the vertical axis here, and you have different allowable levels, 1, 2, 3, and 4. Maybe these represent those n numbers in Rydberg's equation. If you have a big jump in energy, like let's say from level 2 down to level 1, which is a larger jump, well, you're going to get kind of purplish light. So a photon of that light would be emitted from the atom. If you jacked a whole bunch of energy in there and put it into this higher energy level and then let it drop back down, from that level you would get a kind of purplish light. From n equals 3 to n equals 1 is an even bigger jump, so that would mean even more energetic light, even more purple photons. From 3 down to 2, well, that's a smaller jump. And so that could explain the teal color, which is longer wavelength, less energy. And from n equals 4 down to n equals 3, well, that's even smaller jump. So that means even longer wavelengths, even lower energy for that photon. So that could explain the red line. The person who really came up with the first working model that accounted for both the energy level jumps that we were talking about earlier was this guy, Niels Bohr. He's a Danish physicist. This is his basic idea. He says that he's working with a hydrogen atom, let's say, because it's the simplest one. So in the middle there's a proton, that's the nucleus, and then there's 1 single electron. And that electron can be in multiple orbits. It can be in basically infinitely many orbits, but some orbits are not possible. So here we have just 2 of the orbits represented. There's orbit 1 and orbit 2 corresponding with the number n1 and n2. And you could be in n1 and you could be in n2, but you could not be anywhere in between. There were no orbits allowed except for just these orbits. So if the electron jumps down from orbit 2 to orbit 1, it gives off some energy because there's a difference in the amount of energy it has in orbit 2. It has more energy in orbit 2 than in orbit 1. That energy would come off as a photon of light. And since there are a limited number of orbits, there would be limited numbers of kinds of photons, and the bigger the jump in energy, the bluer the light would be. And that would explain the emission spectra of atoms. And the same thing is true for if energy was absorbed. If energy comes into the atom, that could cause the electron to jump up into a higher orbit, but it would only do that if it had exactly the right photon with exactly the right wavelength. And since the energy differences, the energy of a photon is tied to the frequency, that means there would only be certain frequencies, and that means you'd only see certain colors absorbed or emitted. And that explained what was going on with the emission spectra. The details of how he did this are very interesting to me. I find them pretty fascinating and a good illustration of how a creative mind works. And so I would encourage you to watch the little video that's linked here that goes through his thought process in using basic physics to develop a model of the atom. If you don't have time for that, then we're just going to keep going from here and make some descriptions of what he found. What Bohr was able to come up with ultimately is using regular ordinary physics. He found that the wavelengths that would come out of an atom would be equal to 1 over lambda. They would be described by 1 over lambda is equal to B. This is a constant that Bohr discovered, which we'll talk about in a bit, divided by Planck's constant times the speed of light times 1 over a low orbit number minus 1 over the high orbit number. So if an electron transitioned from a high orbit to a low orbit, this would describe the wavelength of light that would come out of there. Rydberg's equation is right down here, and you can notice a similarity right away. These are the same equation. In other words, Bohr's model matches what Rydberg found experimentally in his observations if B over hc is the same as the constant. So let's evaluate it. B was 2.18 times 10 to the negative 18th joules. Planck's constant is 6.626 times 10 to the negative 34th joule seconds. Speed of light is 2.998 times 10 to the 8th meters per second. So if you crunch all those numbers down, here's what you get. You get 10974,214. And this is it's divided by meters because joules cancel out, seconds cancel out, so you have 1 over meters. Okay, so 10 million something, right? Now let's convert this so that it's in the same unit as Rydberg. There's 1 meter for every 100 centimeters, so we're dividing this number by 100, which moves the decimal point over 2 places, so you get 109,742 per centimeters. Look at that number, look at that number. They're almost identical. Everybody was super happy with this model because it explained a way that there could be these energy transitions that matched what we were seeing with emission and absorption line spectra, and Bohr's model became sort of what everybody thought the atom was like. It explained where the electrons were in the atom. This person here, Louis de Broglie, was studying waves, trying to figure out more about electrons, and what he found out was something kind of remarkable. Just like light has a dual nature, sometimes you think about it as a wave, sometimes you have to think about it as a particle, which is a photon. De Broglie found that matter also could be thought of as having a dual nature. In this demonstration here, we're going to start out with water waves. So this is just a water wave generator in a kind of a rectangular tank. Looks like a square tank maybe, with some scale in there. So you can see that there are these regular waves that are being set up here. Now there's a phenomenon that waves do when you put a barrier and leave a slit in it. So we're going to put a barrier here with one slit, narrow the slit up a bit. What you can see is the wave passes through there, and then it sort of changes its shape. It begins to curve. It becomes like a curved wavefront and not a straight rectangular one. Okay, so that's a well-known phenomenon. It's kind of interesting. Now let's try something else. There's another thing that's even more interesting, and that is when we put 2 slits in the barrier. Now we have 2 of these wavefronts that propagate with each other, and those wavefronts interfere with each other. Sometimes they interfere with each other constructively. In other words, the waves kind of both match up, they sync up, and so you get a wave that's twice as tall as the original wave. And then there are other places where they destructively interfere with each other. In other words, you get a wave that's has zero amplitude. So that's a wave phenomenon. Let's try this with light. So let's switch, instead of this being water, let's make this light wave. So we'll turn on this light. So here are light waves. They're going to do the same thing. They're going to propagate through this slit and begin to make this kind of curve pattern. Make this slit pretty narrow. Okay, now let's try a two-slit. And this constructive and destructive interference thing is happening, and you can sort of kind of see a pattern of where that constructive and destructive interference is. But if we put a screen here to kind of project what the light is going to look like, you can see that there are going to be spots where there's going to be higher intensity and then no intensity, and then higher intensity and no intensity as you go from the center of the screen out. And that was a well-known phenomenon associated with waves. So here is an interesting phenomenon that Louis de Broglie was wrestling with. Researchers were finding out that if you could aim a stream of electrons at two slits in this way, they would also behave in the same manner, which didn't seem very particle-like in some ways. So imagine that you had a block wall and you were shooting a machine gun at the block wall, and you had two slits in the wall, and then you had like a big giant piece of cardboard behind the wall. You would expect to see lots of bullet holes right behind where one slit was, and lots of bullet holes behind where the other slit was, and you probably wouldn't see very many other bullet holes because the block wall would stop most of those bullets. However, that's not what they saw. They saw a pattern like this where there appeared to be areas where electrons were hitting a screen that they could detect, and then where there were no electrons, and then areas where there were some, and then where there were none that didn't seem to match up with where the slits were, which indicated to them that the electrons were doing this constructive, destructive interference thing. And then it got really interesting when they slowed down the electron stream to the point where they could just release almost single electrons at once. And a single electron would also display this pattern of destructive and constructive interference, which led them to believe that in addition to being able to be thought of as a little negatively charged particle, like J.J. Thomson's idea, electrons also in some instances have to be thought of as a wave. And then Louis de Broglie theorized that not only electrons do this, but all matter can be thought of as wave-like. And it's just that we don't usually detect that with objects that are large, larger than electrons. De Broglie's matter waves came up with an explanation for Bohr's quantization equation. Remember that equation that he just kind of had to make up, that kinetic energy was equal to n times h times frequency divided by 2? Well, now that de Broglie has this matter wave concept, if you think about the wave of an electron being a standing wave, it sort of gave a lot of support to Bohr's model of the atom. Here's why. Imagine that you have a circumference that's 3 wavelengths around for this orbit, which is really a wave, a standing wave. That could look like the picture that we have here. Or if you had 4 wavelengths around your circumference, that could look like this. 5 wavelengths, 6 wavelengths. You could have any whole number of wavelengths, but what you couldn't have was some number of wavelengths other than a whole number, because it had to be a continuous standing wave. So circumference is some number, n, which has to be a whole number, times the wavelength. But remember, de Broglie's matter wave have a wavelength of Planck's constant divided by m times v. So if we take a circumference, which is going to be 2 pi r, and set that equal to n times the wavelength, which is h over mv, and solve for v, you get that velocity is equal to n times h over 2 times pi times m times r. And that is the same thing that Bohr got for velocity that he substitutes into his equation and then develops the model of the atom. So this was good confirmation that Bohr's model was probably right.